Okay, welcome everybody to my talk. I'm very excited to be here today, actually. And my presentation is going to be about storage and encryption in DuckDB. You might wonder why storage and encryption, but that is because if you really want to understand how encryption is implemented, you will also need to understand a bit, at least at a high level, how DuckDB storage works. But let's first start with me. Who am I, actually? I did a while ago already my master thesis, or my master at the University of Amsterdam, very close here. And when I did my master thesis, I had the opportunity to do that in a database team in Microsoft. It's called Citus Data. And there I did my master thesis about distributed Postgres. So this was actually the first time that I got introduced to database internals and computer science fundamentals, because I never studied computer science. But after that, I decided that I liked it a lot. So I got the opportunity to go to CWI, and there I did basically research at the intersection of databases and security. And eventually, this is what brought me at DuckDB Labs. So currently, I'm a software engineer at DuckDB Labs. And over the past year, I have contributed quite significantly to the encryption features in DuckDB. So to start off with security, how can DuckDB currently secure your data? To start off, I do want to stretch that when DuckDB secures your data, DuckDB only secures data at rest. And that means that data gets encrypted only at the moment when it's written to disk. It has two different ways to do so. The first one is with Parquet encryption. And Parquet encryption already has been there for a while, because it has been released almost 2 years ago, I think, in version 0.10 already. And Parquet encryption, for example, is also used in Duck Lake, because if you use Duck Lake in encrypted mode, then it writes encrypted Parquet files, basically. It's pretty straightforward how to encrypt a Parquet file. You need to add an encryption key through a pragma, and then you can copy a plaintext Parquet file to an encrypted Parquet file. So the second way to secure your data in DuckDB is with database file encryption. And with database file encryption, DuckDB doesn't only encrypt the main database file, but it also encrypts the write-ahead log, and it also encrypts temporary files. In this presentation, I will go all 3 different types of files in the order that I just said. And I will explain also what a write-ahead log actually is and when temporary files are generated. It's pretty straightforward also to encrypt a file in DuckDB. You just need to attach a database. You need to specify your encryption key. And optionally, you can also specify an encryption cipher, which is GCM here. Speaking about the encryption cipher, DuckDB uses the Advanced Encryption Standard, AES. And this encryption standard actually has multiple encryption modes. From these modes, DuckDB, as of today, supports 2 different ones, which are GCM and CTR. And today, I'm not gonna dive deep into how these encryption modes actually work. But the only thing that I want to tell is that both are randomized encryption algorithms. And that means that even when you use the same key and you have 2 or more exactly identical plaintext, this will always result in different ciphertext, if it's implemented correctly. That's an important detail. But yeah, that actually means that when you have an attacker, for example, and it looks at your encrypted data, it can never infer that the underlying data is actually the same. Very short about GCM, because this is the encryption mode that I will be using in the rest of the talk in all my examples. This is an industry standard encryption algorithm. It's used in many systems. And what is important to know is that it uses a number used once or an initialization vector. These terms are also completely identical, like they mean exactly the same, and I will also use them interchangeably. And basically, a nonce is a unique sequence of bytes, and DuckDB generates it itself before it encrypts a chunk of data. And it actually takes care of encrypting all the data in a randomized manner. On top of that, GCM also computes a tag. So whenever it encrypts a chunk of data, at the end it computes a tag. And a tag is basically the same as a checksum, but then with a lot more security guarantees. Going to the encryption keys. So how does DuckDB handle the keys? Whenever you input an encryption key, DuckDB is not directly using this key to encrypt your data. But instead, it puts your encryption key into a key derivation function. This key derivation function also takes as input a database identifier, which is also a random sequence of bytes. And together, it generates a 32-byte secure encryption key. And this key, in the end, is used to encrypt your actual data. And this is also pretty beneficial, because if you decide to use the same key to encrypt multiple different database files, that the actual encryption keys that are used, they are different. So it's just an extra security measurement. I do want to point out, please never use the same key to encrypt multiple different files, because it's not generally considered as secure anyway. Then whenever you encrypt a database file, we do a small trick to check whenever you decrypt it if you use the correct key. So what we do is, when you encrypt a file in DuckDB, we also encrypt a piece of plain text that we know what it is. And in the case of DuckDB, it's called DuckKey, or Ducky. We encrypt this piece of data, we store it as metadata in the database header, and whenever you try to decide to read this encrypted file, one of the first things we do is we look for this piece of metadata, we decrypt it, and if this succeeds, this means that you used the right key. But if it doesn't succeed, we stop the encryption process and we error out early. If your key is correct, we store your key in a secure encryption key cache. And this is a little bit different compared to a regular cache, because we keep exactly track of where your encryption key is stored, and we lock the memory region where your key is stored. This is important so that your key doesn't get accidentally swapped to disk. On top of that, whenever you're not using your key anymore, we make sure that your key is completely wiped out of memory, so it doesn't stay behind. And now going back to DuckDB storage, because you need an understanding at the high level. So whenever DuckDB writes a file, DuckDB first writes database headers. First it writes the main header, and then it writes two different database headers. In the main header, we have a checksum to check if the header is not corrupted. Then we have the magic bytes. We store also the storage version. We store some flags that, for example, also indicate whether or not your file has been encrypted. We store database identifier and some encryption metadata. The other database headers, they store, for example, the iteration count, the count of the blocks that are in the file, the size of the blocks, the vector size, and also a kind of storage version, the serialization compatibility version. But after the headers and after storing some more metadata, DuckDB stores the actual data in row groups. It's pretty similar to Parquet. A row group in DuckDB consists of around 120,000 rows. It's a little bit more, but around 120K. And these row groups are then split in columnar segments that internally is called column data. And these columnar segments, on its turn, are then divided into blocks. And blocks have a very simple structure. They are 256 kilobytes, and they consist basically of a block header of 8 bytes. In the block header, there is the checkpoint stored, and the rest of the block is just used to store your data. Also important to note, DuckDB first tries to compress the data before it actually stores it in these blocks. And these blocks, the size, 256 kilobyte, is pretty efficient for the compression algorithms that we use. And now let's go to main database encryption. There's one thing that I want to point out. The structure on how everything is encrypted is a little bit different in 1.4 compared to 1.5, and I'm explaining how everything looks in DuckDB 1.5, which will be released in around 2 weeks. So if we go back to the main headers, DuckDB actually doesn't encrypt the main database header. It doesn't do so because it really doesn't contain any secure data. Like it's fine if an attacker reads the data that is stored in the main header. And another point is that we store a lot of encryption metadata, and we will need to read that metadata to determine which encryption algorithm is used, how large the key is that is used, and stuff like this. But we do encrypt the following database headers already, and actually all the data that comes after that, everything will be encrypted. Furthermore, we decided to encrypt at the granularity of blocks. This has three main reasons. The first one is that we can easily compress data before we encrypt it, so you will have to encrypt less data. The second thing is because blocks actually have a pretty good size, and this size can perfectly account for the initial encryption overhead. And the third reason is that whenever you compute a query, it's very likely that you probably don't have to read the whole database file, right? And this way you can only decrypt those blocks that are actually necessary to compute the result of your query. To encrypt the block, we need to change the structure a bit. So in this case, we change the structure of the block header. So usually it's 8 bytes, and for an encrypted file, every block header is 40 bytes. So the first 12 bytes, they are used for the nonce. The following 16 bytes are used for the tag. Then you have some empty space, and then the checksum is stored. We actually also encrypt the checksum, so an attacker will also not be able to read that beforehand. This is an extra security measurement, but you can also leave it out. It's not completely necessary, especially if you use GCM. And now going to the write-ahead log. I'm not completely sure if everybody knows what it is, so I will go quickly over it. A write-ahead log basically is an append-only file. And whenever you make a change to the database, this change will first be written to the wall, and before it actually gets propagated into the main database file. So the wall is basically used as a crash recovery mechanism. It's also important for ACID transactions. ACID means atomicity, consistency, isolation, and durability. And it can be used by some database systems to increase performance. In DuckDB, a wall looks like this. So you first have some metadata indicating the wall version. Then you have the database identifier to figure out if the wall actually belongs to the database file that you're reading. And then it stores everything per entry, so per change that you make to the database. So each wall entry looks like this. It first has a length prefixed, because you need to know how long the entry actually is that you need to read. Then it has a checksum to check whether your entry not has been corrupted. And then the entry itself is stored. But most of the times, you probably won't even realize that a wall is written, because the wall is flushed at certain points in time. And the first one is when you trigger a checkpoint yourself. The second point is when DuckDB performs an automatic checkpoint. And this can happen if your wall exceeds a certain size, and DuckDB decides to just write all the changes to the main database file. And the third point in time is when you close the database properly, because if it crashes, the wall will be left behind, because that's the reason why it's there. So how do we encrypt the wall? Because it has a different structure than the blocks that DuckDB normally uses. So to encrypt the wall, we decided to also leave the metadata plain text, because we need to determine whether or not this wall is encrypted. And then we decided to encrypt per entry. And if we zoom in, an encrypted entry looks like this. So we first store the length in plain text, because we need to know how many bytes we actually need to decrypt, and otherwise there's no way to determine that. Then we store the nonce, and then we store the checksum and entry both encrypted, and then we store the tag. Lastly, the third type of file that I'm going to go over are temporary files. I will quickly go over this one, because temporary files, they have actually a similar structure as DuckDB blocks or as a wall entry. So we also encrypt it in exactly the same way as blocks or entries. But temporary files, they are produced when data is spilled to disk. And this might happen when you have a very heavy query, like that needs a very large aggregation or it does a very large join. And usually DuckDB cleans these files up by itself after the execution of a query. But sometimes in case of a crash, they can also be left behind. So we also need to encrypt those files. I do want to mention that we also released a blog post that I forgot to link, but it was released in November. And if you want to know more about either WAL encryption or temporary files, I'm going to refer you to that blog post because there's more explanation about this. And last but not least, I do want to go quickly over the encryption API that we use because some just gave this presentation about extensions. And the main point is that DuckDB doesn't want to have any external dependencies. But we really want to use a proper encryption API, right? So, but OpenSSL is not an option because we cannot link it into DuckDB directly. Not in core, exactly, at least. So the first implementation of encryption that we had with Parquet encryption, for that we decided to use a library called embed-TLS, and we stripped that library and put it in DuckDB core. But the problem with embed-TLS is that it relies on only pure computations internally, so it doesn't leverage any hardware instructions. And as a result, this was pretty slow. So we really want OpenSSL. So we thought about this, and we realized that when people use DuckDB, often they also use the HTTPFS extension that some also mentioned. And this extension on its turn requires OpenSSL. So we did this trick that whenever you are loading the HTTPFS extension, we make use of that by overloading the embed-TLS encryption API with the OpenSSL encryption API. And this way, your encryption will always be accelerated if you load the HTTPFS extension. So we really recommend you to do that. Actually, nowadays, we automatically try to autoload HTTPFS in most cases, because whenever you write to a database, you will need write to an encrypted database, you will need to use a secure random number generator. But a secure random number generator is only be possible if you can leverage dedicated hardware instructions. So for that reason, we disabled embed-TLS for writing encrypted database files. And also very good to point out is that when you use OpenSSL, most of the times you won't even notice a performance degradation when you read encrypted data because it's very fast. Yeah. Coming to the end, the main takeaways from this presentation. So DuckDB is able to encrypt data at rest by Parquet encryption, but also by database file encryption. It doesn't only encrypt the database file, but it also encrypts the write-ahead log and temporary files. Your encryption keys are managed securely, and the encryption incurs negligible overhead. Thank you.
Thank you. Time for questions, and there's one right here.
Thank you. Exciting talk. I want maybe just a question about how these blocks that are encrypted, how they're being scanned. So maybe it's a stupid question because I don't know the design of the scanning mechanism. But yeah, so there are columns and there are blocks that that store the columns, and if there is a procedure that is going to scan the blocks to find the relevant data, and I assume it is going to use the statistics and metadata about these blocks. If the headers do not have this metadata, assumably somewhere else, could you please maybe touch a bit upon that?
Yeah, so if I have this correctly, please, DuckDB people, correct me if I'm wrong. So DuckDB stores, before it actually stores the actual data, it stores a lot of metadata with like what, for example, the statistics of the specific row group are. And based on that, it skips a lot of data, right? And it also knows the location of the block, so it basically knows which blocks it needs to decrypt. Is that clear?
So the metadata is aside. It's not in the blocks themselves.
No, it's not in the block itself.
Okay, cool. Thank you.
Thanks. Any further questions? Jan?
Yes, thanks for the talk, Lotte. I was wondering, does this, because you have to encrypt the whole block,
Yeah.
does that, if you want to retrieve one row from that block, does it encryption allow for random access, or do you have to decrypt the whole block?
Well, theoretically, if you use CTR, you can do it with random access. No, but you need to decrypt the whole block even if you need to only read one value.
What is CTR?
CTR is a different encryption algorithm.
Okay. And
So-
could we choose to use that? Can we like swap it or?
You can, but it's not, like theoretically it's possible, but DuckDB didn't implement it this way. But in general, if you read only one row that is in a specific block in DuckDB, you will need to read that whole block anyway.
Right, thank you.
All right, one question here.
Hello, thank you for your talk. You showed a canary trick that you are using to check if the key for unencrypting a database file is the right key. And I think you said you are using the plaintext word ducky or something.
Yes.
And that's a rather short word. Isn't there a risk of collisions there?
Yeah, I think there always is, but we also didn't want to take up more space. So it's a bit of trade-off between that. But it might be that we change this text at some future point, like at some point in the future. Yeah.
Thank you very much for the talk. Very interesting. You had a slide when you were showing the block encryption, where you were describing the byte size, and there was an empty section. I was just curious about that.
No, it's just because, okay, so we used, oh, sorry, I will go to the slide. Here, right?
Yep.
So you have 4 empty bytes. The reason for that is, well, there are 2 reasons, because the first one is actually that you can change the size of the nonce if you want to. Well, theoretically you can, but we made it now fixed to 12 bytes. But the reason why the block header is 40 bytes is because in the end, we need to calculate a checksum over all the data in a block. And this checksum is 8 bytes aligned. So that's the only reason why we use 40 bytes, basically to be able to calculate the checksum properly.
All right, question from Rusty.
Thank you for the talk. Can you tell us how the nonce is generated? Is it generated randomly once and then incremented, or what's the strategy for that?
Very good question. So the nonce consists of a 12-byte sequence of random data that is generated with a random number generator. And depending on which encryption mode you use, but the Encryption API actually takes care of putting the counter at the end of the 12 bytes. So in total, your nonce is actually 16 bytes. And this counter gets increased every time you encrypt the next 16 bytes. So the encryption algorithm takes, actually the encryption API takes care of this internally.
And then as a follow-up to that,
Yeah.
is the checksum still necessary, even though we have the authentication tag?
No, not strictly. Like it would be an optimization not to do that, but we chose like better safe than sorry.
Okay, great.
So
Thank you.
Perfect. Any further questions to Lotte? Carlo is making himself known, although everyone knows Carlo already. So
How much the database size increases? Because I guess there's some extra data stored, and is also that negligible, or it's
yeah, it's pretty negligible. The well size does increase more because you need to store a nonce and a tag for every entry, and if you do a lot of updates very fast, then this well can increase quite a lot. But for regular database encryption, it like the size overhead is negligible, basically.
all right, last chance for questions. I see one hand. Okay, very last minute.
Thank you for the talk. Are there any best practices of managing the keys of encryption here, like using an external vault that we can plug into DuckDB somehow?
Well, the only advice that I have for you is the more secure the key is that you input, the more secure your encryption will be. Because actually what we did is we are allowing to like have very short user keys. But if you choose to use like a very short key, that obviously has impact on how secure the final encryption is. But yeah, best practices, most people use a KMS and just, yeah, take the key from there, basically.
All right. Thanks again for the speech.